know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. To see the sunrise tomorrow, inspire the world to follow.
Okay, in the curriculum of electric drive, that is E701, module number 5, today our topic is sleep power recovery scheme of induction motor. So let's start lecture number 12 on sleep power recovery scheme. Okay, so when we have studied that rotor resistance control, we have seen that the power is wasted in the rotor resistance, and that's why the efficiency is very poor. Okay, so now instead of wasting this sleep power in the rotor circuit, it can be converted to 50 Hz AC and it can pumped back to the line, and this is basically known as sleep power recovery scheme. Now if we see in this figure, this is a equivalent circuit of wound rotor induction motor. This is a equivalent circuit of slip ring induction motor, or we can say wound rotor induction motor. Okay, now here this SRIM is injected with a voltage VR. So this VR is a injected voltage to the rotor. This is injected voltage to the rotor. Okay, now assuming that a stator to rotor turns ratio is unity, N1 by N2 is 1. Now in this equivalent circuit, if we neglect the rotor copper loss, so PCU neglected. If we neglect the rotor copper loss, then we can say that PM equals to PG minus PR. PM equals to PG minus PR, where this PR is the power absorbed by the source VR. So here PR is power absorbed by source VR. The magnitude and the sign of PR can be controlled by controlling the magnitude and phase of VR. So by controlling this VR, we can control this PR. Okay, when PR is 0, motor runs on its natural speed torque characteristics. When PR equals to 0. Okay, a positive PR will reduce PM. So if PR is positive, PM mechanical power developed will be reduced, and therefore the motor runs at a lower speed. So thus, if we vary PR from 0 to PG, in this range, if I can vary the value of PR, then it will allow the speed control from 0 to synchronous speed. So this will vary the speed from synchronous speed to 0. Okay. Now the polarity of here of this operation, which is shown in this figure, shown by this dotted line. Okay. By this dotted line and this continuous line. This is describe the polarity of gear. This is describing the polarity of gear. Okay. Now when PR is negative, what will happen? So when PR equals to negative, that means VR acts as a source of power. So VR now is the source, acting as a source. Okay. And PM will be larger than PG. So now PM will become greater than PG. So when this PM will become greater than PG, that means the motor will run at speed higher than synchronous speed. So it will run at super synchronous speed. So it will run greater than synchronous speed. Now polarity of VR of speed control above synchronous speed. So when it is run above, so this dotted line will increase the polarity of VR above NS. So this is the change in polarity, plus minus minus plus. Okay. Now when the rotor copper loss neglected, which I have mentioned earlier, PR is equal to the slip power. That means if we neglect the rotor copper loss, PR equals to SPG, because I have neglected the rotor copper loss. This is the basic power flow diagram of induction motor, which we have studied several times in basic electrical and electrical machine. Now speed control below synchronous speed is obtained by controlling this slip power. The same approach was adopted in rotor resistance control. However, instead of wasting power, which I have mentioned earlier, we are feeding back it to the line. Now this slip power recovery scheme can be better understood by two different schemes. One is known as static Kramer drives, static Kramer's drive, and the second one is static Scravius drives. Static Scravius drive. Okay. So these are the two schemes which describe the slip power recovery scheme. Now static Kramer drives only allow operation at sub-synchronous speed, and static Scravius drive allow operation above and below synchronous speed, both. So it is sub-synchronous speed and it is both sub-synchronous as well as super synchronous speed. So this is the basic difference between static Kramer's drive and static Scravius drives. Okay. It is used to control the speed of the slip ring induction motor, which I have mentioned. The speed control of induction motor can be obtained either above or below synchronous speed. I have mentioned stator voltage control and rotor resistance control have poor efficiency. As we know, I have already mentioned in my previous class that why this rotor resistance control have poor resistance, because of the wastage of power at low speed region, suitable for limited application, only for intermittent load. Intermittent load is restricted. Okay. Now, in order to improve the performance of the system, like efficiency and capacity of the drive, which we have done, we have pumped back the slip power to the supply system, and that's how we have increased the overall efficiency, okay, of this slip power recovery scheme. Now, this Kramer drive and Schrevier's drives are further classified into two categories. One is known as conventional slip power recovery scheme, another one is static slip power recovery scheme. Okay, so now first we will discuss Kramer slip power recovery scheme. So as we have mentioned, this type is used to control the speed below the rated speed, and this is, I have mentioned, can be conventional and static. Okay, now conventional drive system improve Kramer's drive system and static Kramer drive system. So we will going to discuss these three. So let's first discuss this conventional Kramer system. Okay, so this is the schematics of conventional Kramer system. So this is the three-phase supply RYB. This is the main motor. This is the slip ring of the motor, and this is mechanically coupled with the DC motor, which is again connected with rotary converter, and this is the slip ring on AC side of rotary converter, and this is the DC supply for DC motor and rotary converter field system. Okay, this type of conventional static Kramer's drive consists of SRIM, slip ring induction motor, DC motor, rotary converter. Now the slip ring of the SRIM is connected to the input of the rotary converter. So it is connected with the input of the rotary converter. Okay, and it converted AC into DC voltage and fed to the DC motor terminals. So if you see here, it's directly connected to the rotary converter where AC is converted into DC, and this DC is directly fed to the DC motor terminal, and this DC motor shaft is connected with the shaft of the SRIM. So this DC motor shaft is connected, mechanically coupled with this shaft of the motor. Okay, so what will happen? This speed of the SRIM is controlled by varying the field regulator of the DC motor. So now if we control the field system of this regulator of the DC motor, we can control the speed of the motor, and this field regulator is connected separate DC bus, as we have seen in the figure. So this is connected in the separate, so this is separate DC bus, this is separate DC bus, and I am controlling the field to controlling the speed of the main motor. So the basic is the slip ring is directly connected to the input of the rotary converter, where this AC is converted into DC, which is feedback to the DC motor terminal, and this DC motor is directly coupled with this main motor, and I can control the field of this DC motor, which is connected with a separate DC bus, and this way we can control the speed of the induction motor. Okay, but mind it, I can only control the speed below the synchronous speed. Okay, so the field regulator is connected separate DB bus, and this is known as constant power control. So constant power control and constant torque control we have studied in our basic classes as well as in the basics of electrical drives of induction motor. Now this is the static Cramer drives is a constant power control method. We should always keep that in mind. In case if the rotary converter is overexcited, it will take leading current which compensate for lagging current drawn by SRIM. So you should this is very important and we should always remember this, that if we can overexcited the rotary converter, it will take leading current which compensate for the lagging current drawn by this slip ring induction motor. Okay, so this is a kind of power factor improvement scheme. So this is a kind of power factor improvement. So using this Cramer drive we can improve the power factor. So this is power factor improvement. We should always keep it in mind that using this Cramer's drive we can improve the power factor. Hence the power factor of the system can be improved, which I have mentioned. So this is only preferred 4000 kilowatt and above power level, this Cramer's drives. Okay, now one thing we should see here, we should mention here, that I have talked about this field control with diode bridge. Okay, so let me draw a curve. So this is speed. Okay, this is VD1, this is VD1, this is VD1, this point is A, this is B, this is IF1. Okay, and this is for IF2, and these two V2. Okay, so this is for alpha 0, this is for alpha greater than 0, this point is A, this point is C, this 2 is VD1 and this is for VD2 and this is IF1. So this figure is field control with uncontrolled bridge rectifier, uncontrolled bridge, okay, and this is firing angle control of control, that is thyristor controlled bridge. The field is constant. Okay, so now if we go through this, so this is you see here, this voltage is VD2, this is VD2, this is my VF, this current is IF, this is my slip power, and this voltage is VD1. Okay, and if you look, this is a diode rectifier, circuit. This is the uncontrolled bridge rectifier, and for this the graph which I have shown, this one. Okay, and now instead of diode, if we use thyristor or SCR, so this is the figure using thyristor or SCR. Same, only the uncontrolled bridge is replaced by controlled bridge. So here thyristor is, so we can here control the firing angle, and I can control the speed. So this is the firing angle control, the second one. Okay, now so this is the two modified or improved Kramer system of the conventional Kramer system. So one is using diode, one is using thyristor. Okay, now in this system the mechanical rotary converter is replaced by three-phase diode bridge rectifier. The slip power of the rotor is fed to the input of the three-phase diode bridge rectifier. It converts AC into DC, and the ripple is filtered by the series connected inductor. This is the basic function of inductor. Whenever we will see inductor in the power electronics or drive circuit, the filtered DC output, that means the ripple free output voltage, is fed to the DC motor armature terminal, and the DC motor shaft is connected with the shaft of the SRM, same as conventional method which we have seen with the rotary converter, and we can control the speed by the speed regulator of DC motor. Okay, so now if diode is replaced by SCR for high power application, which we have seen by controlled rectifier. Okay, control rectifier, and this is the static Kramer's slip power drive. Okay, this is the static Kramer's slip power recovery scheme. So this one is bridge rectifier is used, and this is inverter is used, which fed the AC to DC, and this smoothing reactor nullify the ripple, and this bridge will control the speed of the slip ring motor. Okay, so we can say that rotor slip power is converted into DC in the diode bridge, and this DC power is now fed to the DC motor, which is mechanically coupled with induction motor, and torque supplied to the load is the sum of torque produced by the induction and DC motor. So which is the load torque? It is the sum of production of torque by induction motor plus torque of DC motor. Speed control is obtained by controlling the field current of the DC motor. And here we have shown, which I have mentioned earlier, that in this figure, variation of VD1 and V2 with the speed of two values of DC motor current. One is for IF1 and IF2. So to look, the speed has been reduced, or speed has been increased when I have increased the field current value. It goes from omega m1 to omega m2, and speed control is possible from synchronous speed to around half of the synchronous speed. So that means half synchronous speed. And for larger speed range, we have replaced this with this thyristor bridge. Now the relationship between VD1 and speed can be altered by controlling the firing angle of the thyristor rectifier. We know the voltage VD1 for thyristor rectifier, and in that equation there is alpha firing angle. So if we control the alpha, so you see I am controlling the alpha, and we can change the speed from omega m1 to omega m2. So this is about static Kramer's drive. Okay, and this is the closed loop control of static Krivier's drive, but we have not yet studied the static Krivier's drive. So let me first start the concept of static Krivier's drive. Okay, so now static Krivier's drives. So this static Kramer's slip power recovery scheme is very popular for large pump and fan drives, where range of speed control is limited near but below synchronous speed. And this drive system is efficient, but power converter is very low. This system is called constant torque drive. So we have seen, so the Kramer's drive can be both operate as constant power drive as well as constant torque drive. Okay, and this is the speed torque characteristics of static Kramer's drive. This is the speed torque characteristics. Different firing angle of the inverter. So if we change the inverter firing angle, we can got the torque speed curve but different firing angle. Okay, and this is the advantage. This system of speed control is economical because the rectifier and inverter only have to carry the slip power to the rotor, which is less than the input power to the stator, and it is quite simple and stable method. Okay, and this is the conventional Krivier's drive. This is the conventional Krivier's drive. Okay, and this Krivier's drive speed control of wound rotor induction motor below synchronous speed. In here, a portion of rotor AC power is converted into DC by diode bridge, same as the Kramer's drive. So basically the concept is same. So this is conventional Krivier's drive, and this is the static Krivier's drive. This is the static Krivier's drive. Okay, so this is all about drives. Okay, let me check in the syllabus anything there is left or not. Okay, so this is the basics of Krivier's drives and Kramer's drive. The details we are not going to cover. Okay, so only thing in this static Krivier's drive, we should remember, only thing we should remember, this features requires that slip power in the rotor flow in the reverse direction. So for Scravier's drives, we should keep that in mind, that slip power in the rotor flow in the reverse direction. Now one thing, if the diode rectifier on the machine side, so if you see the figure, if this diode rectifier on the machine side is replaced by thyristor rectifier, the slip power can be controlled to flow in either direction. So if we replace this diode rectifier by thyristor rectifier, then we can control the speed in both direction, and that's why it's operate in two modes. The mode 1 is known as subsynchronous motoring, and mode 2 known as subsynchronous regeneration. Okay, so once I replace the diode bridge with rectifier bridge, the slip power can be controlled to flow in the both direction. Now with reverse slip power flow at subsynchronous speed, the power corresponding to the shaft input mechanical power can be pumped out of the stator. So that such a drive system with bidirectional slip power flow. So the term is bidirectional slip power flow at the term is bidirectional slip power flow, can be controlled for motoring and regeneration, mode 1 and mode 2, subsynchronous and supersynchronous range of speed. So using this Scravier's drive, we can control the speed in both subsynchronous and supersynchronous. Only the constraint is we have to replace this diode bridge rectifier with this thyristor rectifier, and this is the static previous system. Okay, so this is all about my slip power recovery scheme. In our next class we will solve some problem, and this is the closed loop control of static previous system. Okay, this is the closed loop control. Okay, so this is all about. Okay, so these are the reference book. You should study from this, from BK Bose, GK Dubey, and also online resources like SlideShare, Scribed, Wikipedia, Circuit Global, to mention a few. Okay, thank you.